So let's start off and consider nozzles and diffusers. We'll start off with the whole energy balance, except we'll get rid of the summations on the mass flows because we've only got a single inlet and single exit. Now, my argument for which terms that we don't really need will be as follows. The mass that's flowing either through the nozzle or the diffuser doesn't stay in it very long, and so there won't be appreciable heat flow per unit mass. There's no moving parts here, so there's no work interaction, so we can immediately cross off all of the heat and work terms. Further, we don't know anything about the elevation difference, and even if you have a nozzle in the back of the jet and the jet's going straight up, nozzles on jets aren't all that long, and so the potential energy difference between the inlet and exit of the nozzle is negligible. So we can cross off those GZ terms. We don't need those. So that's all we're going to get rid of. It's quite a bit. That simplifies the equation down to simply a flow stream in that has both enthalpy and kinetic energy, and a flow stream out that has enthalpy and kinetic energy. And so if we realize that the mass flow rate in and out are equal, because we're assuming that this nozzle or diffuser is operating at steady state, we can cancel the mass flow rate as well. For a nozzle, the incoming velocity is usually a whole lot less than the exiting velocity, and therefore the square of those two terms are even more different. And in fact, what it really means is that since the incoming velocity is so low, the kinetic energy that it brings in, the v squared over 2 term, is so small we can just neglect it for nozzles. So for nozzles, our energy balance tells us that enthalpy coming into the nozzle, some of it will leave as enthalpy, but some of it will be converted to kinetic energy at the exit of the nozzle. For a diffuser, the opposite applies, where the incoming velocity is relatively high by comparison to the outgoing velocity. And so the outgoing velocity, once you square it and divide it by 2, it's not even worth talking about. So the kinetic energy at the exit, it's basically not there. And so we say that the incoming enthalpy plus kinetic energy becomes all enthalpy at the exit. What about turbines and compressors? Well, with the turbine and compressor, usually there's not enough heat interaction to worry about. Sometimes there is, but usually there's not. The kinetic and potential energy changes are also usually negligible, and so we end up with an interaction between work and enthalpy. In the case of a compressor, the work output is 0, right? A compressor consumes work, it doesn't produce work, and so we could write that the compressor equation is the power flow rate in required is equal to the flow, well, not the flow energy, but the fluid power generated within whatever stream is flowing through the compressor, in this case air. Now there's something wrong with this energy balance that I've got. Can you see what it is? Do you know that most compressors actually have heat loss during compression? The reason for that is that it makes it require less work. And you'll see why that is a little bit later. So I shouldn't have crossed off that heat loss quite so quickly if I wanted to model this particular compressor. So I could go back to the original equation and just include the Q dot out, not cancel it, and still have Q dot out in this. And what you would see is that Q dot out would appear on the right-hand side of the equation. So you have to be careful about these equations. Most of the time, the simplified form that I give you will work fine. Sometimes you'll have to go back to the original equation and say, oh, I got to pick up this term because it's something that's actually there. For the turbine, the opposite is true, where turbines don't consume work, they produce work, and basically they transform fluid power into work. And you can see that where the power output is equal to the mass flow rate times the enthalpy drop across the turbine. Notice that in the compressor, the enthalpy at the exit has, or the stream at the exit has higher enthalpy, whereas for the turbine, the stream at the exit has lower enthalpy. So these are just opposites of one another. One of them puts energy into the fluid, the other one extracts energy from the fluid. Well, what about a throttling valve? The device that I said is so wonderful because it gives us air conditioning. It makes air conditioning possible. Well, for it, you might think, well, how do throttling valves work? Well, let me tell you a little bit about them. Usually what happens is you have a refrigerant come in that is a saturated liquid. And as the refrigerant goes through the throttling valve, the pressure drops. And so what happens is some of the liquid boils off and goes into the vapor phase. What ends up happening, though, is the vapor and the liquid cool down quite a bit. Their temperature drops like crazy. And so let me ask you a question. Do you think there's any heat transfer? Should we keep the Q terms or let them go? Well, if you think about it and you know there's a temperature drop, you might be tempted to say, well, there must be some heat transfer. The temperature has dropped. Well, actually, most of the time these devices are insulated, and the fluid doesn't spend enough time in the device to really transfer significant heat per unit mass. So actually, we need to cross off those terms. And you might say, well, wait a second, what's going on? How can the temperature drop? I'll show you in just a second. Stay with me. What about the work term? Well, again, inside of a throttling valve, there's usually not moving parts. There's not pistons and things that are moving. Even if there is in a thermostatic expansion valve, it usually moves and then stays essentially within a range. It doesn't contribute a significant work amount. So most of the time the work terms are also crossed off. It turns out that also the kinetic and potential energies are typically crossed off. Potential energy you can understand because there's not going to be much elevation change across the throttling valve. You might be tempted to say, well, wait a second, that's not really fair, because if the exiting stream has now a lot of gas in it, that's going to take up a whole lot more volume. If the pipe size is the same, there's going to have to be a higher velocity of flow at state 2 than there was at state 1. And yet, if you do the math, what you find is that the kinetic energy, even though yes, there's a higher velocity of flow at the exit, the kinetic energy difference is not worth talking about, really. And so we end up with an equation where it looks like everything has just been thrown away. Even the mass flow rate can be thrown away because it just divides 0 by the mass flow rate and it's gone. And so our energy balance reduces to enthalpy in equals enthalpy out. You might say, well, wait a second, that doesn't make any sense because the temperature dropped. Yes, it's true, the temperature dropped. How can we understand this? How can we have the same enthalpy in and out and yet the temperature has dropped? Well, remember the enthalpy consists of two parts. There's the thermal energy piece, which is kind of like the temperature, and then there's the flow energy piece, which is kind of like the pressure. Well, one goes up while the other one goes down, doesn't it? You might say, well, wait a second, both the temperature and the pressure drop at state 2, so how can you say that at state 2, one of them has gone up? Well, notice that it's not just the pressure in state 2, it's the pressure in state 2 times the specific volume in state 2, and it's the specific volume in state 2 that has increased drastically. Therefore, the flow energy in state 2 is much higher than the flow energy in state 1. So all these throttling valves do is trade off thermal energy and flow energy. As a matter of fact, they give up thermal energy to develop flow energy, the PV term. Now, for incompressible fluids, when it can't change size and that pressure drops, well, then the flow energy has to go down, right? So then the thermal energy goes up. If you ever dealt with a dynamometer, for example, say you've got a car that you've added, souped it up, and you want to see how much power it develops. Did you know that when you take it to the dynamometer, you put it on it, and you make that car do work turning that drum? Basically, that drum is a hydraulic pump, and the hydraulic pump is just taking in hydraulic fluid, compressing it, and then that fluid just gets dumped across a valve. So basically, the fluid pressure just drops across a valve, a flow restriction, and what happens to the temperature of the fluid is it goes up. Before that fluid can go back in and be recirculated to go again, it has to be cooled. And so what you do is you put that oil through an oil cooler and then back to a tank to kind of mix it in with whatever's already there, and then draw the oil through the pump and continue the cycle. So all the energy being produced by your car, all that power, is going to hot oil, or basically heating the air ultimately in a heat exchanger. That's where it all ends up. So for an incompressible fluid, where the fluid does not evaporate, where there's no evaporation, then there's just a conversion from flow energy to thermal energy. On the other hand, if you have a compressible fluid, you kind of got to figure out what will happen. But if you have something that is a liquid that's going to boil off, a phase change, well, then typically what happens, depending on the property of the particular fluid, a certain amount of thermal energy will be converted to flow energy. What about mixing chambers? How could we analyze those? Well, for those we can't get rid of that summation sign on the inlet and exit because we've got more than one inlet. Okay, we can get rid of the one on the exit, the out. But what about heat transfer? Well, you look at this and you might be tempted to say there must be some heat transfer. After all, we got a 140 degree fluid coming in and a 50 degree fluid coming in and then a 110 degree fluid coming out. And so isn't that heat transfer? Well, no. Remember that heat transfer is an energy flow due to a temperature difference across the system boundary. The system boundary is just the mixing chamber. And so there's no heat flow here. In fact, mixing chambers are frequently insulated. Not in your home, but in industry. For large mixing chambers, they're commonly insulated because you don't want to lose heat or you don't want to gain heat. So how can you say that there hasn't been any heat transfer? Isn't there thermal energy transfer from one mass to another as they mix due to a temperature difference? There is, but that's taken into account in the mixing internally because the exiting stream has a different enthalpy than the two incoming streams. So we'll get rid of the heat transfer terms, we'll get rid of the work transfer terms. Again, there are no moving boundaries, so those terms will go away. Typically we'll get rid of the kinetic and potential energy changes. And so again we have something that looks a lot like a throttling valve, except that we could have multiple inlets, multiple exits, and typically we would have two inlets, one exit. So the mass flow rate at the exit state 3 times the enthalpy that stream carries quantifies the rate at which that mass carries energy out of the control volume, or in other words, the power flow rate out of the control volume by mass. And then the other two terms come from the fact that there are two inlets. I've switched the equation around on you, I'm sorry, I should mention that. So the inlet terms are on the right-hand side of the equation now, and the outflow is on the left-hand side. Okay? But there are two streams coming in, both of which carry power into the mixing chamber. And you might look and say, well, one of them's 50 degrees. That doesn't carry any power in. Yes, it does, because that temperature is above absolute zero. Therefore, it does carry power in. Okay? It's just not as much as the other stream coming in, and it's not as much per unit mass as the stream flowing out. Now, technically, it actually could be a higher power flow rate if the mass flow rate at state 2 was much higher than the mass flow rate at state 1. Then even though it's lower quality thermal energy, in other words, lower temperature fluid, it still could carry more power into the mixing chamber. Now we could also write a mass balance here and say, since this is operating at steady state, the flow rate coming in stream 1 and stream 2 must be equal to the mass flow rate leaving in stream 3. And we could then make a substitution to get rid of the exiting mass flow rate, m.3, and finally here's our resulting energy balance. If you remember all these derivations, great. If you don't, well, just hope that you don't have anything where there's, say, a heat loss or a heat gain with one of these mixing chambers. Okay? So what's in the box is what you really need to know. And what we really see here is that mixing chambers just mix the enthalpy of all streams together. That's what they do. Heat exchangers. What about a heat exchanger? Well, actually a heat exchanger will reduce down much like the mixing chamber did. So again, by the same arguments, we would get rid of all of the heat transfer. You might say, hey, wait a second. This is a heat exchanger. How can you cross off any heat flows Q? Well, notice that the heat flows with the system I've taken occur internal to the heat exchanger. There's no heat flow across the system boundary out to the environment. Rather, there's heat flow internally, but that heat flow will be taken care of by the enthalpy change observed in the fluid streams. Now, just like the mixing chamber, we end up at this equation, but now we have two inlets and two exits, and so we can talk about the mass flow rate at A, or basically the power carried in by stream A, and the power carried in by stream B. Both of those streams coming in for A and B to the right and at the top, those two streams carry energy into the heat exchanger, whereas the two exiting streams carry energy out of the heat exchanger. Okay, so the first two terms, again, I've flipped it around on you, I'm sorry, but the two terms on the left now, m.A HA out plus m.B HB out, those are talking about the power carried out in the two exiting streams for A and B. whereas the terms on the right hand talk about the power carried in by those two fluid streams at A and B. If we rearrange this a little bit, we can solve for the mass flow rate of A in terms of the mass flow rate at B, and note there are no heat transfer terms here because there's no heat flowing across the system boundary. Now you may look at that and say, you know, that seems like cheating. Okay, well let's do this. Why don't we set up two different systems? One will be this white dotted system, and the other one will be a green dotted system. Now it looks like there's two green dotted systems, but I'm thinking of this heat exchanger as just being a round thing. So it's a pipe within a pipe, and we're just looking at a cross section of it. So that green section is actually revolved around. It's a so-called annular region. It's like a thick donut. It's a cylinder with a hole in the middle of it. Okay. Now there's heat flow across the system boundary. Certainly you can see that there's heat flow from the hot stream, fluid B, to the cold stream, fluid A. So we could write an energy balance for, let's say, stream A, because we know that stream A comes in with less energy and leaves with more, and most of the energy that it gains is certainly enthalpy, right? Flow energy and internal energy. The heat transfer rate would just be Q dot. We don't know exactly what it is, but we know it's coming into the system. And if you think about the energy balance and go from the big one to simplifying it out, getting rid of the work terms and the kinetic energy and potential energy terms and so forth, this is where you'll end up. Now, the other system, the green system, is losing heat. Okay, so Q dot B out of that stream would be equal to the enthalpy change of the stream times the mass flow rate of stream B. But obviously, if heat leaves the fluid B, it must enter fluid A because the system is operating at steady state. We can't accumulate or deplete energy within the control volume. So if it leaves stream B, it must enter stream A. Therefore, these flows are equals and opposites of one another, right? Putting these two together, guess where we end up? Exactly where we were before. The heat transfer rates just cancel out, and we get an equivalent equation to what we had on the last slide. What about duct and pipe flow? What would we do there? Well, a lot of times in duct and pipe flow, the kinetic and potential energy terms go away, but frequently that's all we can get rid of. Usually these don't involve multiple inlets and multiple exits, so we can simplify, get rid of the summations, and only consider a single inlet, single exit system. But we usually end up with this type of equation, and you have to decide which other terms can be crossed off.